This is Team 4's final presentation, where we analyze and redesign a drill press. Our team is Brendan Hessling, Eddie Kim, Rebecca Lara, Dhruv Patel, Sam Wasserfall, and Josiah Wong.
Background on a tabletop drill press, which are commonly used to drill holes into materials such as metal, wood, and plastic. A motor drives the spindle to rotate an end mill or drill bit to create precise holes within the working material. A drill press provides control and precision to the user with low cost and minimal training when compared to a mill. The primary consumer of the drill press are those who own small workshops for metalworking, woodworking, garages for cars, and general engineering needs. These are also purchased by secondary consumers such as hobbyists and DIYers who work on at-home projects outside of the professional setting. The global market was $889.4 million with a compound annual growth rate of 4.15% in 2022. There are an estimated 254,000 drill presses sold globally per year based on an average price of $3,500. Pictured here is an exploded view of the drill press with its various components. Note the screws and nuts are not shown within this image.
Within the function analysis system technique, or FAST diagram, we describe the one main task function for our tabletop-sized drill, as well as the basic and supporting functions to answer the question, how does the product or the drill press perform the task function of creating holes?
Using both the fishbone assembly diagram from the assembly sequence and the FAST diagram, we created a function component mapping matrix to determine the functional purpose of each component of a drill press. The names of each component, excluding the fasteners, can be found in the leftmost column. Each terminal function from the FAST diagram can be found along the top row. If there is an X in a cell, it means that the function is realized by the component in the corresponding row. Using this matrix, we are able to determine the functional importance of each component of the drill press. Using the function component mapping matrix and the bill of materials, we organize each of the components of the drill press into the quad chart. The chart organizes the components into 4 categories based on cost and functional importance. We determine the cost of each component using the bill of materials, and the functional importance of each component using the function component mapping matrix. The components that are of high cost and high functional importance are the ones in which DfMA should be applied.
For the product family design, we'll cover a few slides relating to the functional differentiation table, component commonality table, CAD for modules for primary and secondary customers, common interface, and product family assembly diagram. The functional differentiation table is based on the FAST diagram branches shown in the slides before. The functions that differ between the customer groups are just size and hold product. The components commonality table references the function component mapping matrix shown before, and the modules that change are the table, neck, and table lock.
As we can see in these 2 figures of the CAD for the primary and secondary customers, the primary customers has a drill press with an enlarged size in the neck, table, and table lock, and additional holes in the table for mounting and holding product. In the secondary CAD file, you can see a reduced size in the neck, table, and table lock, and only 1 hole in the table for mounting and holding the product.
The column piece shown is the Common Interface Platform CAD. This enables the plug-in of module parts. The bottom section connects to the base while the top section connects to the module piece neck. The table lock is tightened around the larger middle shaft of this column. This slide shows the total assembly of the 2 different CAD modules for the parts table, neck, and table lock, showing the differences in size and difference in ability to hold parts. The table primary CAD is larger in size with additional holes for mounting. The neck and table lock primary CAD is larger in size with no additional changes. This is the product family assembly diagram. The assembly starts with the base of the column and then splits into 2 branches when it reaches the table lock. The original and modified assembly sequences are identical, with the exception of the table being the last place in the assembly sequence for the modified assembly.
We analyzed the assembly to find out which part has the biggest impact on the manual assembly time. We decided to choose the base plate and the table lock. We also selected the column, lever handle, table lock lever, and the neck because there's opportunity for part consolidation. As we can see from the quad chart, these parts are ideal for a redesign because they either have high manufacturing costs or high functional importance or even both. The assembly efficiency was 25% and 5%. As we can see from the functional matrix, the base plate, column, and neck shares the same function of maintaining control and isolating motion. As for the table lock lever, and lever handle, they share the same function of positioning product and defining position. By having the same function, it makes it a lot easier to consolidate the parts. Starting with the base plate, column, and neck, it took 64.2 seconds to assemble. We improved the design for manual assembly by consolidating the base plate, column, and neck, and we also eliminated the fastener that attaches the column to the base plate. We also removed some parts that were unimportant to the function to make the part more symmetrical. The holes in the middle of the column were also pre-threaded for easier insertion. For this part, there are no major changes to the part function since it could still maintain control and isolate motion. As for the manufacturing cost, there are some effects since there was increased cost in manufacturing due to pre-threaded holes and more parts to fillet to avoid sharp edges. we were able to reduce the assembly time from 64.2 seconds to 41.45 seconds. As for the table lock lever, and lever handle ball, it took 34 seconds to assemble. We improved the design for manual assembly by removing the table lock lever and lever handle ball. We removed those parts because they didn't serve its function of defining position to its best. We also moved the screw holes to a more easily accessible location, and we made the part more symmetrical. The screw holes were also slightly larger for easier insertion of screws, and this part was fixed to one location rather than being adjustable. As for the park function, there were some effects. Since the table lock is now unable to position products at different heights and is locked at one position, the function was now accounted for from the spindle subsystem. As for the manufacturing costs, we expected there to be a decrease in material costs since there would be less parts to machine. We were able to reduce the assembly time from 34 seconds to 24 seconds. Overall, the design efficiency with the modified manual assembly parts increased from 25.75% to 29.17%.
For the automated assembly, we selected the spindle subassembly to improve for automated assembly. We observed that many parts share functions such as maintain position, for example, such that there may be opportunity for part consolidation, as well as many parts sharing low functional importance, such that there may be repetitiveness and consolidation opportunity. It costs $12.61 to automatically assemble the system. And so we consolidated the flange, the spindle cone, and the spindle cone sleeve into one part and eliminated all fasteners to reduce overall part variety. We also redesigned the top of the part to be more symmetrical. We added a feature on the sleeve to facilitate orientation, allowing for the bars to slide with a larger tolerance entrance immediately after insertion, but adjust to align the bars correctly during insertion and to avoid any adjustments needed. We added a feature to the new combined spindle cone sleeve for easy insertion. And we referenced the following design guidelines that suggested these modifications. All these modifications reduced the cost from $12.61 to $6.04. There's no impact on product functionality, but we expect an impact for more expensive machining of the new combined spindle cone sleeve part, but that is offset by the cheaper assembly cost.
We chose to analyze the table lock, which was shown in manual assembly. For the table lock, the underlined and bolded dimensions fulfill the functions of maintain position and position product shown in our FCMM. The tolerances for the critical dimensions are 10 thou to reflect standard die casting tolerances. This is the candidate manufacturing chart for the table lock. We recommend aluminum to be used in die casting for this part. This is because if we were to go with machining, many more additional processes would be needed. Key dimensions are shown, and critical dimensions for the sleeve are bolded and underlined. These relate to our sleeve's FCMM function of maintain position. These critical dimensions have a tolerance of 1 thou to reflect standard machining tolerances. This is the sleeve candidate manufacturing process table. We recommend steel because this is part of the spindle, which must be durable. It also needs a high surface finish. We chose to go with machining because of the geometry of the part itself. The redesigned part follows the same function as before, but with a symmetric design and fewer parts to manufacture and assemble. Additionally, we used uniform wall thickness throughout the part, added fillets to avoid sharp corners, and added 2 threaded holes to integrate fasteners, shown by 8 in the top picture. This resulted in a decrease in manufacturing and assembly cost. As mentioned, this redesigned part has filleted edges and a uniform wall thickness to suit die casting better. All fillets are 1 mm, and the changed dimensions are shown in bold and underlined. The sleeve price increased slightly due to the fact that we increased the center hole diameter to standard drill size, shown by DfMC3. This was done in order to standardize dimensions according to DfCM3. Additionally, we added a radius to the corners to allow for the use of an end mill alone, as opposed to using other processes afterward to create the corners. Fillets will in turn reduce the amount of tool changes and setups needed. These changes are shown by DfMC10 and 15. There is no change in product function and assembly cost. The redesigned sleeve has filleted corners, as previously stated, to avoid additional work after milling, allowing for a 2 mm end mill to be used for the entire group. Additionally, as previously stated again, the center through hole is a standard drill size for simplicity. The changed dimensions are shown in bold and underlined. Here's the Hubs quote, assuming a 20% profit for the sleeve before and after the redesign. As expected, Hubs also shows a more expensive manufacturing cost per part after the redesign. There is a large discrepancy, however, between analytical methods and the Hubs cost, because analytical methods more deeply analyze the part, whereas Hubs make certain assumptions, possibly creating this discrepancy. The material choice options in Hubs are not exactly the same as what we chose in our analysis as well. Hubs is extrapolated data, which does not accurately reflect the cost of the part.
In order to provide further benefits for both the consumer and the environment, we also implemented a product service system. We plan to allow consumers to rent the drill press instead of purchasing the tool. This will be more convenient for consumers since they can pay a daily, weekly, or monthly rate rather than purchasing the product, which will save them costs. The shared use will also decrease need for manufactured units. We also plan to use recycled materials, reducing the impact on the environment and consumption of resources. This will allow for us to buy back old products, refurbish them, and sell them for a lower price. To conclude, we were able to decrease the table lock assembly time by 10 seconds and the base assembly time by 22.75 seconds. We were able to save $6.57 per assembly. Our DFM for the table lock saved 23 cents per part. Our DFM for the sleeve resulted in an increase in cost, however we were able to standardize dimensions and reduce tool changes in manufacturing. If we were to redesign from the beginning, we would try to consider costs from changing manufacturing processes,
as well as make additional improvements to components that we did not address during DFMA.